The universe in 20 minutes. The universe started about 13.7 billion years ago with a Big Bang, a period of rapid expansion of empty space. Shortly after the bang, a further period of inflation occurred, lasting a fraction of a second, causing the universe to expand exponentially. From this experience, the universe formed four components: space, time, matter, and energy. We have developed two theories to explain these phenomena: relativity and quantum theory. Relativity mainly deals with the large-scale structure of the universe, and quantum theory deals with the small-scale structure of the cosmos. Matter has three components: ordinary matter, dark matter, and antimatter. Ordinary matter constitutes about 4% of the known universe. The main constituents are atoms, which are subdivided into protons and neutrons at the core, and electrons orbiting the outside. Most chemistry, electronics, and information technology can be defined by the behavior of the electron. The electrons exist in increasing energy shells and are negatively charged. Like many objects in the universe, they not only have charge and mass, but they also have spin. Electrons exist in spin pairs that affect one another, even when separated by millions of miles. Protons are in the nucleus and are positively charged. This state of atoms has a twin state where the electrons are positively charged and the protons are negatively charged. This is called antimatter. When matter meets antimatter, they destroy each other. Fortunately for us, there seems to be more matter than antimatter in the cosmos. There are three quantum forces which tie these subatomic particles together. They are the strong force, holding the protons and neutrons together in the nucleus, the electromagnetic force that holds the electron in orbit with the nucleus, and the weak force that accounts for atomic decay and the emissions of radioactivity. These forces have four associated particles called bosons. The boson, named the gluon, works to hold the nucleus together. Photons are connected with the electromagnetic force, and the W and Z bosons are associated with the weak force. Recently, scientists have concluded that particles that didn't initially contain mass needed to come under the influence of a field that gave them mass. This field became known as the Higgs field, and the boson associated with this field is the Higgs boson. Bosons can be seen as force-carrying particles. There are many other subatomic particles, such as quarks and leptons, that are known as fermions. The quarks go to make up the protons and neutrons, and the electron being an example of a lepton. There are a total of 16 subatomic particles making up the standard model of particle physics. The history of quantum theory goes back to Max Planck, who discovered that quanta are discrete packages of electromagnetic energy that are emitted when electrons go from a higher energy state to a lower one. Later research concentrates on the uncertainty of a particle, discovered by Heisenberg. The more you know about its momentum, the less you know about its position, and vice versa. Quantum theory also integrates the concept of duality. Most theorists now acknowledge that waves and fields explain how the universe is made, but when matter is observed, it reacts like a particle. The very observation of subatomic particles seems to affect how they behave. Light acts like a wave, but under observation it behaves like a particle known as a photon. The famous double-slit experiment demonstrates this. Metaphysics takes these ideas even further, suggesting that consciousness actually affects the physical universe of space, time, matter, and energy. At the other end of the scale, the theory of relativity comes into its own. This theory is divided into two parts: the special and the general theory. They deal with large-scale structures like stars, galaxies, and black holes. The special theory deals with energy and matter, where energy can be converted to matter and matter can be converted to energy. This is expressed by the famous equation E equals mc squared, where c represents the speed of light at 186,000 miles per second. c squared represents an enormous number, and the equation shows that a very large amount of energy comes from a very small amount of matter. This process of converting matter to energy is called thermonuclear fusion, and involves the nuclei of atoms being fused together under enormous temperatures and pressures. Our Sun is using this process to irradiate heat that is keeping us alive. It fuses 4 million tons of hydrogen atoms to form helium atoms every second. The process has been mimicked on Earth with the development of the hydrogen bomb. The Sun, however, has been doing this for nearly 5 billion years, and will probably go on for another 5 billion years. The special theory has other features such as time dilation. Einstein, the creator of the theory, suggested that as objects get faster, their time slows down. He based this on a constant that states that the speed of light is always the same, no matter what your situation in the universe. He postulated that as you approach this speed, your watch would become slower and slower until at light speed it would stop. A trip into space at high speeds would find you much younger on your return than your friends you left behind. Matter also increases as you get faster and distance shrinks. However, this speed cannot be reached, as nothing containing matter can ever reach the speed of light. Einstein went on to develop a further theory called general relativity. This theory suggests not only is space a product of 3 dimensions, length, breadth, and height, but space-time is the product of 4 dimensions, length, breadth, height, and time. His research demonstrated that when matter interacts with space-time, it distorts it, or curves it, and the effect of the distortion of space-time we call gravity. Gravity is a universal force, like the 3 subatomic forces mentioned earlier. Oddly enough, at a quantum level it is extremely weak, much weaker than the other 3 forces. It only manifests its strength around enormous objects like stars and galaxies. Gravity was discovered by Newton, who told us that the force of gravity was directly proportional to the mass of 2 nearby objects, and inversely proportional to the square of the distance between them. In extreme cases, Einstein's theories have overridden Newton, but in everyday situations on Earth, Newton's ideas still hold. I previously mentioned that matter existed in 3 states. We can surmise that the matter of atoms is one of low vibrational energy, and there are many aspects of the universe as yet not fully understood. One of these is dark matter. This cannot be seen, as by its very definition is dark. Physicists have estimated it would count for about 23% of the universe, derived by the fact that the speed of stars orbiting the edge of galaxies are as fast as in the center. Without dark matter, they doubt the galaxy would have enough gravity to hold together. Dark matter probably contains weakly interacting massive particles, WIMPs, not yet detected. After the Big Bang, there seemed to be a slight uneven distribution of matter in the cosmos, which might explain how 13 billion years later we have volumes of enormous mass and volumes of nearly empty space. I always think it is like money. Most of it always ends up in the hands of the few. Our 2 main theories are backed up by other supportive theories. One of these plays a crucial role in the design of the cosmos, and that is the theory of thermodynamics, contained in 3 laws. The first of these laws is actually the zero law, that states that uneven systems will eventually find an equilibrium. The first law tells us that matter cannot be created or destroyed, it just changes its form. The final law is defined by the process of heat flowing to cold. This states that order flows to chaos, which we call entropy. As the universe gets older, entropy increases. You will see later that this law has a direct bearing on the possible outcome of the fate of the universe. The cosmos also contains constants. Planck's constant, the founder of quantum theory, the charge and mass of subatomic particles, the speed of light, absolute temperature, the coldest anything can become, Newton's gravity constant, Einstein's cosmological constant, and many others. There is, however, one constant I would like to focus on, as it defines the history, the present and the future of existence. This is Hubble's constant. Hubble discovered that the universe was expanding, and as it expands, it is accelerating. We know this because of one peculiar aspect of light and sound that is called the Doppler effect. When a train is approaching you on a station, the sound it makes is compressed, but when it passes, the sound is stretched. This distortion also works with light. In galaxies, the red end of the spectrum of the light they emit is extended, which shows that they are moving away from us and each other, suggesting the empty space in the universe is expanding. From this, we have deduced that in the past, the whole universe was contained in one point called a singularity. Some believe that this singularity was actually a cosmic black hole located in another universe, which became a white hole in our universe. If you remember earlier, I said that there were 4 components to the cosmos: space, time, matter, and energy. I said that there are 3 types of matter. There are also 2 types of energy: energy and dark energy. Dark energy makes up 73% of the universe, which is having the effect of ripping the universe apart. More of this later. As we progress through the cosmic time experience, we need to look at the life cycle of stars and how they are related to the atomic structure of matter. Stars are formed under huge temperatures and pressures from nebula and collapsing gas that are compressed by gravity. This turns on the thermonuclear reactions of converting hydrogen to helium. The last embers of this reaction will drive the star to one of 3 final outcomes. These outcomes depend on the initial size of the star and its corresponding gravity. Small stars like our Sun will eventually collapse into a white dwarf, which is a star that has enormous density because the nuclei of the atoms are compressed together. The space between the nucleus and the electron has been overridden by gravity. The electrons are surrounding the perimeter of the nuclei, but cannot enter due to the Pauli exclusion principle, stating that 2 particles cannot occupy the same quantum state simultaneously. With bigger stars, the gravity overrides the exclusion principles, causing the negative electrons in the atoms of the star to be forced into the nuclei, which will neutralize the positive protons in the center of the atom and form neutrons alone. This is called a neutron star. Neutron stars are very much heavier than white dwarfs and are detected by cosmic radiation called pulsars. In much bigger stars and at the centers of galaxies, a further process occurs. This form of gravity is so great that the neutrons of a neutron star would overcome a further extension of the exclusion principle and become black holes. The neutrons have imploded inside one another. This entity has such strong gravity that even light cannot escape its clutches. Black holes are detected by radiation known as quasars. So where are we in our quest to understand the universe? We have reached a point to try to understand a theory of everything and to find the ultimate fate of the universe. A theory of everything would link the 3 subatomic forces with the theory of gravity, the quantum with the relativity theory. To answer this, we need to devise a new theory called string theory. The effect of mass on curved spacetime has been detected by gravitational waves, which slightly distort matter. All the forces have a wave-like nature. In string theory, physicists suggest that at a very small scale, smaller than the quarks that make up a proton, there is an entity known as strings, tiny amounts of vibrational energy that vibrate at a frequency defining all the particles around the standard model. This can only work if the entities were vibrations at different dimensions, of which there are 10. This would bring the force of gravity under the umbrella of quantum mechanics, without violating the theory of relativity. The most popular way of describing this is known as M-theory, but there is still much work to be done to fully understand and develop an equation of everything, the grand unified theory. So what of the fate of our universe? There are 3 possible outcomes suggested. Firstly, there is the Big Crunch theory. This suggests that the total sum of matter and dark matter will cause gravity to finally pull the universe back into a singularity, i.e. the Big Bang in reverse. The red shift of stars and the cosmic microwave background radiation is evidence of the Big Bang, and so this process could be reversed back to a cosmic-sized black hole, which in eons of time to come might vomit its matter out again as a white hole, thus creating a new Big Bang. This expanding and collapsing universe might go on forever like a heartbeat. The second alternative is for the universe to go on expanding, but to slow down. This universe, the Big Chill suggests, the dark energy overrides the dark matter, but there is a limiting factor to its overall deteriorating effect. The favored view these days is the Big Rip, where the cosmos will be eventually torn apart by the effects of dark energy, accelerating the universe's expansion to the point that every galaxy, star, and even atom will be torn to shreds. Scientists have postulated that this energy might be the effect of other universes existing alongside ours with different dimensions and structures. Could it be possible to travel to these universes and into parallel or different realities? Would portals of travel, such as wormholes, be the way to other forms of existence? As yet, we don't know, but can only summarize. We live in a time where knowledge is expanding exponentially. The more we understand, the more questions we throw up. We will never understand everything, but what gives existence its meaning is that we are able to ask the question why. Peter Bull, FRAS. Narrated by Chris Macari.